All right, so what we're going to talk about in this video is tsunamis. And so we've discussed tsunamis briefly when we talked about some hazards that were caused by earthquakes. And so we know that that's one way that we can develop tsunamis. And there are other ways that that can happen, but for the most part, when we see big tsunamis, they're usually associated with earthquakes, and that is because there's a lot of earthquakes that occur, much more common. Another way, of course, is we can get landslides, either splashing into a body of water or underwater. Even asteroid impacts and things like that can generate tsunamis. But let's look at some of that information. So a tsunami is different than just a tidal wave, right? Or maybe just like a surfer's wave, right? Like a wave that you'd see at the beach. And so what we see for tsunamis is a large displacement, or I guess it doesn't have to be large, a displacement of a body of water. And here's some ways we can trigger those, of course. We're talking about earthquakes for the most part is a very common way, and because there are a lot of earthquakes that are in ocean basins or in bodies of water, we can displace that water through movement of the crust, landslides. So we can get underwater landslides, so there are steep slopes under the ocean basins, and once again, an earthquake could trigger that, or just the instability of a steep slope failing. Moving down slope can displace water. We can have volcanoes that either explode, erupt, or collapse. Once again, the collapsing of material into a body of water is like a big cannonball, so we're displacing water, or a blast can displace water. And then, of course, we talked about there's some impacts from objects, and so they're not very common, but we can talk about an impact causing a large kind of tsunami wave. And the example you might see is, there's an asteroid that potentially killed the dinosaurs, or at least led to their kind of demise, and that object struck in water back 65 million years ago, and there's some computer generated models that show these enormous tsunami waves that were generated from that impact. So certainly that is a way to do it, but they're not as common. So we focus more on the earthquake story. And so here's some tsunamis that have been recorded or seen or experienced. And you could see that there's different causes, but a majority here are caused by magnitude, 7, 8, 9s, big magnitude earthquakes. And so you could see some of the damage here. The exemption here is Krakatoa, which you kind of watched that video. It still generated a very large tsunami, but it wasn't related to an earthquake. And so some of the more recent ones that we've seen that have done a lot of damage were this 2004 Sumatran earthquake and a 2011 Japan earthquake. Those were very large. You could see by their values here. And they displaced a lot of water and generated some very large tsunami waves. All right, so we talked about, the causes, most common cause, earthquakes, right? And they need to be usually fairly large. Now, of course, they have to be underwater, right? So if I have an earthquake, like let's say the San Andreas Fault, where it's a transform or a strike-slip boundary, there's two problems with that. One is most of the movement is horizontal, so I'm not up and down, and a lot of that fault is on land, and so that's not going to impact or create a tsunami. And of course, if we look at other boundaries, like let's say where the Himalayas are being formed, we have two continents slamming into each other. There's no ocean there. We get earthquakes there for sure, but there's no ocean to displace. And then finally, of course, remember we have these boundaries that are under the ocean basin, but they're not convergent. We have divergent plate boundaries down there. Once again, there's not a big uplift. There's not a big pushing up of the crust, displacing water. So although there are some earthquakes that occur at divergent plate boundaries, we typically don't generate a large tsunami there. And so what we're really looking at is convergent plate boundaries, right? This is the place where we generate these really big kind of tsunamis. And so They're super fast when they're out in the deep ocean. So there's a little formula that you can look at that determines the speed of a tsunami wave. And it has to do with the depth of the ocean. So the deeper the ocean in general, the faster the wave is traveling. But as it gets close to shore, what happens is the frictional forces of the shallower kind of seabed slow down this wave, and it starts to pile up, and we have these waves that increase in height as we get close to the coastline. So out in the deep ocean, they're fast, and they're generally not as tall. The wave heights aren't very tall. But as they move inland and they compress a little bit and the water gets shallower, they slow down. We get this building up of the wave height, and then of course it can crash into the coastline and move inland very far, and lots of damage occurs there. And so the other thing to be aware of is these aren't like we talk about surfer waves where they, like if you go to the beach and you see a wave, okay, it comes, it crests, it crashes, it swoops up the coast a little bit, 10 feet or 20 feet, and then it goes back down. Because these waves that are generated from these big earthquakes have long wavelengths, when they strike the coast, they can move inland for a mile before they recede. And so this is the other issue that we run into with tsunamis. And you'll look in some of the videos, hopefully, be able to see that impact where the waves move really far inland. And of course, there's factors that involve how far inland it moves, certainly the height, but also, the elevation of the coastline. If it's relatively flat, it can move in very far. If it's fairly steep, you could slow down that energy and it wouldn't move in as far. And so we want to evaluate kind of those things when we look at tsunamis and the tsunami damage. And so then just to kind of reiterate this point that where do we get these big earthquakes that can generate tsunamis? And so here's a couple images I want you to kind of recall. So this is a plate boundary map that shows the plates. It's also showing volcanoes, but the thing about that is a lot of these volcanoes that are illustrated on this map are generated by subduction. These are the plate boundaries where we get big earthquakes because there's a lot of stress being stored, and we get this uplift under the ocean basins. So this is also a plate boundary. The blue here, these are all divergent plate boundaries. They're pulling apart the crust. There isn't this dramatic uplift when there's a breakage there or an earthquake. But here, all along this place where we have subduction, we can get this kind of thing happening, right? So there's stress from the two plates colliding, there's distortion, then there's this release of energy as the plates and rocks rebound back to their original position. And in doing so, there's some vertical movement here that displaces the water, generates a wave, and then it moves inland. So when we look at the boundaries here, the boundaries between these two plates isn't here on land, it's submerged, it's under the ocean here. And so that's why we can generate these tsunamis. So generally, tsunamis are occurring in this red area here and not in the blue area. So the big ones we just talked about, there's an Indonesian one, that's over here. Japan over here. There's worries of Cascadia, so the Pacific Northwest over here. Hawaii. How about Alaska? There's a big Alaskan earthquake that generated a tsunami. Down here in South America, there was earthquakes that generated big tsunamis, all because of their tectonic setting, and that's this subduction story. And so I'll just to kind of even emphasize the point even more, here's just a little video, right? We're showing this kind of compression, right? The stress, because they're convergent. The distortion here, so we're having this deformed plate, and then once this can't handle that stress anymore, it moves and it causes an upward motion, which then generates a tsunami. And so this is the story for our big earthquake generated tsunamis. I think there's one other thing I'll show you really fast here. Did I miss it? It's kind of right here. So this shows, sorry for that. Let's go here and I'll move around. So what else did I want to talk about? Oh, I know. So here we have an underwater right? Landslide. And so we're moving this material from here to here. So what happens to the water above it is it depresses because we take that away. And that's how we generate these tsunamis that occur under the sea, under the ocean, right? So these underwater, of course, material that just slams into the ocean also displaces water. So we've got that going on too. And then, of course, I'm going to jump around here and do this for you. Remember, too, that these tsunami waves, because it's an interface, this is the boundary between the two plates. So in a side view, this would be subducting. When we get failure all along this boundary here, we're generating a large area of a tsunami. So it's not just like, boop, right there, right? It's a huge area when we kind of have these big earthquakes at these plate boundaries that occur. Okay, let's get that out of there. Go back to our craziness. And so here we go, just another image showing how the tsunamis are generated. It doesn't do a great job of showing the boundary, so that's why I had those previous images. But the idea is that we displace water, there's some uplift there. The wave is fast and furious out in the deep oceans, and it's not as tall, the wave height. But as we come closer to the coastline, the fact that there's some drag here, some frictional, some slowing down, it causes the wave length to kind of squish together, compressing it. And because these wavelengths are initially very long, remember, this is maybe going 500 miles an hour, the front of the wave slows down before the back of the wave, and that causes kind of a bunch up, if you'd like, right? So that causes the wave height to rise up. So when it gets to the shoreline, it can be very tall. And there's been documented, heights of big tsunami waves coming in and, up to 100 feet tall, which would be just horrifying if you saw that coming your way. And so this is why, of course, they are a big hazard that we want to kind of talk about. So that was the main kind of, earthquakes. We want to understand why that happens, the boundary types we would expect those from, and the locations that might be at risk. There are, of course, some other ways, landslides, and they can be due to a couple reasons. Earthquakes certainly can trigger that. But the fact that we have very steep, unstable slopes, they can just fail because of time and gravity. And so there's a few examples of that we can talk about. One of the kind of the big ones that was just related to a failure of a rock face was this Alaskan example here. And so if we kind of look at that, there was this little bay here, and there was a failure of this rock face. It looks something like this on the bottom right. And it basically splashed down into the bay and displaced a huge amount of water. And so the very initial wave came across and impacted the land here. And you could see that the height was estimated by the amount of trees that were stripped off. And that's what this yellow is showing on this map view here, is the wave height based on the removal of the trees. And so the initial wave height was basically taller than the Empire State Building when it impacted into here. And so it did some damage all along this whole bay. It was confined just to the bay because once it exited the bay and got into the Gulf of Alaska, then it dissipated and really didn't have much impact because we're only affecting a very small area, not like a large earthquake that would rupture a 100-kilometer interface and generate a wave, that is much bigger than what we see here in this little landslide, but obviously devastating if you happen to live here. Luckily, there are only a few people here on boats, and, there's not a lot of people that lived here, so it wasn't as big of an impact, but still terrifying. And then when we talk about some of the hazards, a lot of these seem obvious, but we'll run through them kind of really quickly. Obviously, there's structural damage, right? So as a wave moves through and impacts, the weight of this water is enormous. It strikes the, buildings and everything in its way, and it can decimate those. And you can see from the images here how much damage potentially a tsunami can do. This is from the 2004 Indonesian tsunami that was generated by a large earthquake at a subduction zone. And so just a few more images. This is from the Alaskan tsunami. So a lot of times when we have these big earthquakes, the case for, the Alaskan example, a lot of the deaths were caused by the tsunami and not so much by the earthquake itself. And so that was probably also true for the Indonesian earthquake and tsunami. And so these can be fairly devastating. The other thing, of course, it's bringing in lots of water. And so not only do you have this damage from the impact, but the water moves inland and settles into low-lying areas and floods those areas. Even though there is a receding of the wave after it kind of moves inland, a lot of that water is stuck in low-lying areas, and it's a flood hazard, of course. And so then you get flood damage from water kind of going into homes and structures and all those kind of things. Drowning, then, of course, is another issue because, of course, we're bringing in lots of water for a variety of reasons. You can get, people being impacted by the initial flood because it's violent and fast moving, and there's debris trapped in this huge just mess of water. And so even if you're like, yeah, I'm a great swimmer, this is not going to help you in a large tsunami event. Mostly you'll be struck by objects or things like that that might cause some issues. And of course, with the extra water and flooding, drowning is always a possibility when it comes to tsunamis. Other things we can kind of think about, erosion, right? So we don't necessarily think like, oh, there's a tsunami, I'm worried about erosion. But when it's hitting these coastlines with beachfronts, there's an enormous amount of energy. And so you can totally kind of structure the entire coastline because the water comes in and strips away a lot of this loose material. It can also undermine, abutments for bridges and things like that. It's happening quickly because it's fast-moving water. Debris impacting these structures too, of course, along the way. And then we get these secondary effects that are always an issue when we have these major disasters. Fires are always an issue because we're breaking things and causing gas leaks, and we have trouble getting to areas because once they catch on fire, then it's hard to move around, fire trucks and things like that. And of course, in these cases where a lot of potential structures can be overwhelmed, sometimes water treatment plants can be overwhelmed. Then you have stagnant water, and then so water supply becomes a problem. And then, of course, we run into some disease and things like that. So there's certainly some other aspects we want to kind of think about when we talk about tsunami damage. And then, where am I worried about tsunamis? Well, we kind of looked at that previous image, but subduction zones are my biggest, concern. Certainly volcanoes can have some impact, but the other thing to think about is subduction is generating our volcanoes, so there's some overlap there for sure. And so if we look at a little map to look at kind of areas at risk, even though the plate boundaries aren't on here, they really are. It's where you see red is really where we have subduction. And so this red area is subducting plates, which means that the contact between the ocean and the other plate is under the ocean basin. So movement along those interfaces would displace water potentially, and we could generate large tsunamis. So let's be clear that every earthquake on a subduction zone doesn't have to generate a tsunami, but certainly that's where we would expect one if we have large earthquakes. These other places are low risk because they're not really in an area where we have these boundaries that are really the one of the more common ways we can generate tsunamis. So we look at tsunamis around the world, how frequently they occur. This is by decade, and so kind of an old image here or some data, but it kind of shows you maybe the idea of how many tsunamis are generated. So, on the order of 100 maybe is an average as we kind of go through here. But, we have a lot of ones that are non-damaging. So small. Certainly you can get a tsunami and it might be, a foot tall. Moves inland, an extra 20 feet. That's not a big deal. But certainly every decade, we have several tsunamis that are big enough to do some damage. And rarely we get these really huge ones. And like I said, the 2011 Japanese earthquake, the 2004, those were pretty big tsunamis, really big. And one of the reasons were that big 9 magnitude earthquake. So those are rare, which means the big tsunamis are rare. And so we can certainly have other ways to generate tsunamis. A couple of years ago, Anak Krakatoa, so not the original Krakatoa, but the one that's growing there after the big explosion from Krakatoa. As it grew, it was unstable, and there was a landslide failure that generated a tsunami that impacted the coast there and did some damage for sure. So we can certainly get from those, but they're not as widespread and typically not as damaging as these big, large magnitude earthquakes that we see. So what can we do about it? Well, one of the things we do is we can build buildings that can survive kind of the impact of the water, and of course then elevate people above the water. And so that's what you're seeing in some of these structures here. We have these in some places where you have a high tsunami danger. There's these structures, and when there's an earthquake, there's potentially a tsunami. If you can't get very far inland, you can climb up this structure, be above the wave height of the incoming tsunami and potentially survive that. Or structures that do double duty, where they start as a parking garage, or in some cases a school, but they also are built to withstand the impact of some type of tsunami wave. So you can get up high, you can be secure, and so like I said, normally it's some structure that can be used in everyday life, but it also doubles as a way to get up above the elevation of a tsunami wave, and can also take the force of the waves striking the structure. And of course, mapping is another way that we can mitigate the hazards, because why? We know where the danger is. Just like mapping landslides, just like mapping earthquakes, if we know where the dangers are, then we can prepare, right? So based on our knowledge of subduction zones, this is the higher risk places. We can make these global maps. We can, of course, make more local maps. Where are the hazards here, along this portion of North America? And we can even get, down to these small bay areas and determine, based on elevation mostly, because we're going to look at, okay, this place has earthquakes. It can generate an earthquake potentially up to a 9. What kind of elevation would we expect from a tsunami wave coming in? And then we're going to look at the elevations of the land surface. Lower places would be at higher risk. Higher places, not so much. And so then we can make a map, and then we can say, all right, these are the things we need to worry about. These are the areas that are at high risk. We need to build buildings that can, take that impact, or we need to do other things like that to keep people safe, for sure. In some cases, we change the land use. So this is an image of downtown Hilo. And so some of the areas after this impact from the tsunami were kind of designated as parks. Instead of having people build their structures, it's kind of this idea of doing double duty. When there's obviously no tsunamis coming in, it serves a purpose. But it's low-lying, and it's, a very high-risk tsunami area. And so instead of building structures that could potentially, collapse or harm people if they're inside, we make nice little outdoor areas that serve as double duty, and that's another way that we can reduce some of the damage or hazards. And of course, like all the other hazards, knowledge, education, right? This is key to survival. And so if you're aware that you're in a tsunami area and you know what to do, right? So if there is an earthquake, potentially a tsunami could follow. And so do you know what to do? Do you know where to go? And so as long as you can educate the public, we can reduce some death from an injury from that, for sure. And a lot of times in these areas, you'll see signs like the one in the previous slide, or something like this, that has a map that says, look, if you're in these areas and you feel an earthquake, you need to evacuate those areas. You either go to these structures here if they're close by, you get up in elevation if that's possible, but you want to remove yourself from that area. And of course, if you're here, we don't want to run in this whole, orange area, because it's the same hazard, right? So we want to get up to some high elevations and get out of the hazard area. Now, sometimes structures are used, and so we have tsunami walls that can take the impact of the wave hitting it, and they're high enough that it can absorb that energy and deflect it. And so sometimes that's useful. Certainly, there are images in the Japan earthquake where the tsunami walls just weren't even high enough because it was so big. The waves actually overtopped those. So not common because that was an enormous earthquake, but when you're building these things, you prepare for, what you can afford to build sometimes. And so they are useful, but maybe not in the most extreme cases. This is just an image of that. Or we have this kind of image of just these rocks that are kind of built out into the bay to help protect the bay. We also have some natural kind of barriers. And so when you are in coastlines where there's lots of, let's say, mangroves and things like that, and there's these trees and shrubs that are kind of in this coastal community, these are energy absorbers, right? As a wave comes in, it can dissipate some of that energy, slow the wave down. This can keep it from moving inland too far, and of course, reduce the wave height. So these are, useful things to have. And even in some cases, there's these onshore barriers. So this image here is showing you this is a low-lying area, and there's some structures up in here. And so the wave would be kind of funneled up here into this area, this valley. And so there's a structure here that allows the water to drain out into the ocean. So it's almost like a little dam here, but it's always open. When there's a tsunami warning, it could close down and act as a wall, and it could prevent water from moving up into the valley and flooding the structures there. What about prediction? Can we predict? Well, we go back to the same issue we run into with earthquakes. Prediction is very difficult because we know there will be a tsunami potentially happening at certain boundaries, but we don't know when. And just because there's an earthquake doesn't mean there's automatically going to be a tsunami. But the good news, at least now, is that we have warning systems in ocean basins that are susceptible to tsunamis. And so this dart here is basically a buoy that is floating on the ocean, and it's tethered to the ocean floor. And of course, when it moves up and down, beyond normal moving up and down, and of course related to an earthquake, right? So we can sense the earthquake through our seismometer. We're like, oh crap, there's an earthquake. We know one's coming. We look at now we go check our buoy sensors. And if we see a deflection, we could then send a warning. So like everything, if you're far enough away, I can give you a warning. Potentially, maybe it's, a couple minutes. That could be enough, certainly, to move you to higher ground. Because it's not instantaneous, remember. These boundaries, remember where the two plates connect, these are offshore. And they might be, 50, 100 miles. So even though this thing's moving super fast, it would still take 5 to 10 minutes to maybe hit the coast if it's very close. And so we can give warnings for that. And so that is a way to predict, if you will, if a tsunami is going to impact a coastline. Because certainly an example, and I think when you watch the video about tsunamis, in the 2004 Indonesian earthquake and subsequent tsunami, there was no warning system in that ocean basin. And so this is why the death toll was super high. Besides the fact that it was just enormous, there wasn't warning for people. They didn't know. Now, of course, there are some there, but we didn't know. And, in the 2011 Japanese large tsunami, they knew. So devastation was horrific, but most people, not everybody, of course, but people were able to get to higher ground because they did have a warning system in place. All right, so what do we know? Well, obviously we can't, prevent them from happening, but like everything, we want to minimize. And so how do we do that? Well, we have detection and warning systems. We just talked about those are useful for sure. Structures, we use that, right? Whether it's, offshore, onshore, buildings, things like that. And then these hazard maps, these how far inland would a wave, an average tsunami wave generated from an earthquake move, and then we can find the areas that are in danger, right? And then we can make a plan for that. And so I know I've referenced a couple different events The two big ones that stand out because they were so large were this Indonesian tsunami. So in your homework, you're actually going to work on a little information about this event and use some Google Earth stuff. But, this is the big factor here. It was enormous. So it displaced there's a lot of vertical displacement, uplift, right? So we moved a lot of water, and you could see, right? And we moved it not just vertically, but it was a long rupture. So a lot of water, a large wave generated. And here's the key for this one. No system, and this is why the death toll was really so high here. But of course, at a subduction zone, and that's what we would expect from these very large tsunamis that occur. This is just a map that's showing kind of the wave as it moved through the ocean basins. And if I remember right, it was recorded in all the ocean basins everywhere. Now, of course, in some places it was tiny, but it was obviously most devastating right here. So India right here, and of course Indonesia all along here were highly affected by this big tsunami wave. And even though it takes time to reach these places, it was still big enough to move all the way across, hundreds, thousands of kilometers of ocean and still do damage. Right? As it moves farther and farther away, of course, it gets weaker and the wave heights reduce. But close by, lots of issues with that. And then, of course, the Japanese earthquake that happened in 2011. Once again, super big. Once again, it ruptured a large area. Once again, it's a subduction zone. And so these big waves were generated. Here, they did have a lot of, you hate to look at, death numbers, but you could see a comparison between what happened in Japan and what happened in the Indonesian earthquake and subsequent tsunami. And so a lot of that was preparedness. Japan is aware, it had warning systems, it knew what was coming, and so it was able to kind of survive a little better. But there was some evidence that suggested that in some places the wave height, 132 feet, that's ridiculous, right? And this is the, same thing. The wave was just moved through all ocean basins, was recorded, doesn't have to be huge everywhere. But this idea of a large area being ruptured and a big wave coming in, and so it moved inland, all these places were affected because it's a large rupture zone. And then here's some tsunami events, and it gives kind of some, fatalities and where a lot of the damage was done based on some of the information recorded from that event. What else have I got for you? And the same thing, here we look, the tsunami waves were recorded on the west coast, moved all the way across the ocean basin. Certainly, they're pretty high here. And so remember, it's not only the wave height, it's the depth of the water and the shape of the coastlines. So a lot of times what happens is that some of the waves get funneled in. So you have to be really aware that just because one area gets hit by a tsunami and it doesn't seem so bad, you could go down the coast 10 miles and the tsunami height would be higher and the effect would be more damaging. And that's because the shape of the coastline can dictate the height of the wave. And sometimes it can funnel it, and there's a lot of weirdness going on. And there's not just one wave, right? It's multiple waves come in. So just because you run away and you see the wave come in, you're like, yay, I'm going to go back down to, you got to be careful because those can continually come in. You can get multiple waves that come in. And lastly, we want to be concerned about the Pacific Northwest. And why is that? Well, there's evidence that a large earthquake occurred there and there was tsunami damage. There was no one living kind of in the Pacific Northwest that could record that, but it traveled all the way across the Pacific and impacted Japan, and people have lived there for a lot longer, so there were records. And they had a tsunami that came and hit the coast, but there was no earthquake. And through cool science, we were able to kind of connect those two and realize that this area is potentially similar to Japan and similar to Indonesia, could generate these large earthquakes, which means could generate large tsunamis. And is the Pacific Northwest prepared for that? Probably not, because although we knew earthquakes happened there, there wasn't a big kind of tsunami story until we started to understand the kind of plate boundaries and what's happening there. And so, once again, our same kind of preparedness goes into play there now that we're aware. Structures are being built, education is out there, maps are created so that we can reduce some of the issues that might come along if there's ever an earthquake that happened and a tsunami was generated. And so if you do feel an earthquake and you're on a beach or low-lying area, right, run away is the method of survival here. And so you want to move to higher elevations. Hopefully there's signs and directions and where to go. And remember, there can be multiple waves that come in, and in different areas can be affected by different, wave heights, because the shape and size and depth of the coastlines vary as you move up and down the coast. That affects the wave height and how fast it runs in. So that's what we got for tsunamis. So it's not hugely new. There's a lot of overlap for stuff you've already learned, plate tectonics, subduction zones, this kind of stuff. It's really this new idea of displacing enough water to have the energy move through. A little bit about, depth of the ocean affects wave height and wave speed that you want to be aware of, and kind of what to do and how to prevent some of the damage that may occur for tsunamis. Okay, so hopefully that was not too bad, that you were able to understand most of the content there. But as always, if you're struggling a little bit or you're not sure, what to focus on, or having some difficulty understanding some of the content, I can't speak, concepts, please don't hesitate to ask lots of questions.